Welcome everyone. Welcome to our Web EV Club. So good afternoon, good morning, good evening, and good middle of the night to some of you. So we really appreciate our worldwide audience. And so today we have a special treat. We have Wyatt Vreeland from the National Institute on Standards and Technology in the US. So Wyatt is somebody that whom I met a few years ago. And every time I meet with Wyatt, who is joining us from Guam right now, if I understand correctly.
Yeah. This is a beach in Guam. We have a private jet that I just took over there. It's less crowded over here, and it also we have a lot of UV light and heat.
Excellent. So I mean, it's perfect. So
and I took a shot of bleach this morning, so I should be good to go.
You're following all the guidelines, Wyatt, and it's great for me every time I get to meet with you, because afterwards I always feel that I'm a little bit better informed and maybe even a little bit smarter for having met with you. And I think that our audience is going to feel the same after your talk today. So I've seen a little bit of what you're going to share, and I think it's very exciting, and it's going to be informational to everybody. Wyatt, it's all yours.
All right, thanks, Ken. Let's see if I can make this work here. So this is actually the first time I have given a talk from my kitchen. Normally I do it in a room. So let's see if we can make this work. So can you guys see my slides now? Does that look good?
Very good.
All right. So like Ken said, we met a couple of years ago. He came and gave a talk at NIST on some HIV virology work that he had done. One of our RNA chemists had invited him out. We chatted briefly about AF4. We had lunch. And next thing I know, we wrote a grant together. Oh, actually, Ken wrote it. I just put in a few slides. And that grant was funded. And so now we are collaborating. We share, we have a postdoc that works between us. And so I'm not actually going to talk about extracellular vesicles today. I'm going to talk about liposomes. And you can think of a liposome as like the most simple, most boring extracellular vesicle you could ever think of. But that being said, before we get into the talk, let's see, how do I go to the next slide? There we go. I have to put this disclaimer in here that I'm going to be talking about certain commercial equipment, instruments, and materials. These are identified to give context, and they're not intended to be exhaustive reviews of what's out there. Also, anything I say is not an endorsement or recommendation of the National Institute of Standards and Technology, and any opinion or views stated, both oral and written, are solely my opinion and not an official opinion and statement of the National Institute of Standards and Technology, U.S. Department of Commerce, or the U.S. federal government. All right. So a little bit about NIST, because we're kind of something like a university, but we're also a little bit different. We're located about 40 kilometers north of Washington, D.C. We're on something kind of like a college campus, about 2.3 square kilometers. We have a staff of 3,000, and of those 3,000 staff, 2,100 are PhDs. And we also have an additional 50% of the staff that are visiting scientists. So these are people that work in our facilities, collaborate with us, do research, write papers. They just are funded by another agency, by university or another national lab. And we have an annual operating budget of give or take $1 billion per year that funds all of that. It's really a fun place to work. We've had several Nobel Prizes in the past, mainly related to low temperature physics, optical trapping. Our first Nobel Prize was Bill Phillips in 1997. Then Eric Cornell got a Nobel in 2001 for, again, Bose-Einstein condensates. These are low temperature clusters of atoms that exist in a unique state of matter. Jan Hall got a Nobel in 2005 for optical lattice trapping. Dave Wineland got a Nobel in 2012. Dan Sheckman got the Nobel in chemistry in 2011. He's not actually a NIST employee, but the work that he got the Nobel for was done at NIST on some crystal structures, or amorphous crystals. And then John Kahn got the Kyoto Prize, which is a material science award that's one rung below the Nobel. So we're overdue for our next Nobel. So hopefully we'll get one in the next couple of years. So the idea is that we are an institute of standards and technology. And the idea is that the standards, the development of standards, higher accuracy standards allows us to develop more accurate and more precise technology. And that more accurate and precise technology then allows us to create better standards. And so one of these examples is what Jan Hall got his Nobel Prize for. I don't understand the details of this, but it's an optical comb, and it allows us to do time and frequency measurements that are accurate plus or minus 1 second per order billion years. So those are the new atomic clocks that NIST is going to be producing in the near future. They're not live yet. We're still on some older technology, but those are coming online soon. Okay, so that was a brief introduction into NIST. Now I want to start talking about what a liposome is. This is probably redundant to most of the people in the audience, but we'll still go through it. So a liposome is composed of an amphipathic phosphatidylcholine or some kind of a lipid group where we have a polar head group, we have a hydrophobic tail. When these things are introduced into an aqueous phase, they self-assemble into a bilayer structure where the polar head groups are faced towards the exposed aqueous compartments. And the hydrophobic tails are shielded from that by packing against one another. And what that allows us to do is to encapsulate an aqueous interior that's segregated from the aqueous exterior. And so you can think of it kind of like a small little bag, a small little container. And here's actually a fluorescence micrograph of some fluorescent lipids that are swelling in an aqueous phase. And you can see these individual liposomes starting to bud and swell as a lipid film that is hanging on a filament starts to hydrate. So it's kind of I think it's a pretty picture, kind of like a cluster of grapes. But eventually these guys would fully hydrate and they would blub off and float off into the aqueous space. So normally in a good situation, these guys are uniformly dispersed throughout the aqueous phase. So how do we make those? There's a lot of traditional methods of making them. The first one the previous micrograph that I showed you, that's a thin film hydration where we just put a mixture of the lipids down onto a solid surface, add an aqueous phase on top of that, and they kind of just form liposomes spontaneously. Then there's other techniques where we can take the lipid and dissolve it in some kind of an organic solvent where it's fully solvated, and then mix that organic solvent into an aqueous phase and slowly remove it. As that aqueous phase organic phase disperses away or mixes with the aqueous phase, the lipids become less and less soluble, and they begin to form into liposomes. Detergent removal is a similar thing where we use a detergent to solubilize the lipid and to slowly remove it. And so each one of these methods has its pluses and its minuses. The mechanical method here, the thin film hydration, is probably the simplest to do, but gives you the most heterogeneous liposome preparation in that you'll have lipids that vary in their lamellarity, in their size. They're incredibly polydisperse. You basically just get a bunch of lipid garbage. The organic solvent removal techniques are a little bit, will give you a more homogeneous preparation, but any of these techniques that you use, there's some kind of post-processing after you make the initial crude preparation to homogenize the preparation, either through extruding it through some kind of a porous membrane, implying a lot of sonication or sonic energy to break the articles apart. And so when I was a postdoc at NIST, way back in the early 2000s, we said, well, wouldn't it be cool if we used a microfluidic device I had a lot of experience in microfluidics. I was just getting into liposomes. And so what I'm showing you right here is an optical picture of a microfluidic device next to a, this is a 5-crown Czech coin, Czech Republic 5-crown coin. It's about the size of a US quarter, just to get you an idea of the scale. And if you see these lines here, those are actually small little tubes that are on the order of a few hundred microns in diameter. And what we do is we introduce fluid through these circular ports, and we flow that fluid through there. And if you can see right here, we can flow in fluid B right here, flow in fluid A bifurcates, comes back and then sandwiches onto fluid B, and we get something like a sheath flow. And so what I want to show you is how we implement a solvent injection method in this microfluidic system. So here I'm showing that microfluidic cross T. And what we're going to do is we're going to flow in from the north and the south our aqueous phase. And then we're going to have on the left side or the west side, we're going to have our lipids. We're going to dissolve those in an alcohol, usually ethanol, stream where they're fully solvated. And what's going to happen is that that alcohol stream will get sandwiched in here. And as those two streams come down here, we're going to be operating in a very low Piclet number where all of the mixing is going to be completely diffusive, no convective mixing. Those two phases will begin to interdiffuse. The lipids will no longer be fully soluble, and they will start to form into liposomes. So I want to show you how this looks in actual optical micrographs. This is an actual picture of it working, where we can see this is just reflected light. We can see the refractive index mismatch between the water phase and the alcohol phase, and that persists as we go down the channel until the alcohol and the water phases have begun to mix, and there's no longer that strong refractive index difference, so we don't see any attenuation in the reflected light. If we dye the alcohol stream with a dye, we can see that persists. We've actually dyed, in this case, the lipids with a red fluorophore. So you can see that these persist in the center because they're actually forming into liposomes where their diffusion coefficient goes to essentially 0. And then if we dye the aqueous phase in green, we see again that persists through here. So we have a nice, beautiful laminar flow, low Reynolds number. It's purely viscous flow. There's no inertial forces at play here. All right. And so how do we think this is working? So what we think is happening, and this is work that was done with a postdoc of mine back in 2010 named Justin Zook. He is now actually a permanent staff member at NIST, and he is the champion of what we call a genome in a bottle. So he basically makes full human genomes and puts them into a bottle and sells them, or NIST sells them at cost. So what we think is happening is, this is again that same micrograph. Here we've got mathematical modeling, some finite element modeling, where we have the alcohol lipid stream, and then this false color image is the alcohol concentration, and so you can see the alcohol concentration diminishes as we go down the stream. And we think what is happening is that those lipid molecules, as the solvent becomes more and more polar, begin to self-assemble with one another and form these lipid rafts. And at some point, these lipid rafts get big enough that they can start to fold and flop and fold over on one another and then form into a complete vesicle because this exposed hydrophobic tail here is entropically unfavorable. And so to minimize the entropy of the to maximize the entropy of the system, it actually helps to close that vesicle. And now here's the really cool part. we said, okay, so let's start playing with some parameter space. Let's start changing the total flow rate of the system. Oh, sorry, I got ahead of myself. We'll get back to that. Let's see, how do I go back? So that's how we think we make liposomes. Now I'm going to talk about how we characterize this. So I think this is probably one of the things that is going to be most interesting to you guys. This is a workhorse technique in our laboratory called field flow fractionation, or FFF. Most commonly there's different flavors of FFF, just like there's different flavors of chromatography. But the one that's most widely implemented currently is asymmetric flow, field flow fractionation. So I'm going to talk to you a little bit about how that works and how we use it to analyze liposome samples. Keeping in mind that these same techniques can be used to analyze extracellular vesicles and other biological colloidal particles that aren't always amenable to analysis with traditional chromatography. So story goes, so this technique was actually invented by a guy named Cal Giddings, who was a professor at the University of Utah. He first described the paper in 1976 in a Science article. And the story goes, although there's question of its accuracy now, that he was an avid outdoorsman, and he was fly fishing one day in the fall, standing in the river. And what he noticed was, as the leaves were falling down into the river, the leaves that fell in the middle of the stream moved more rapidly than the leaves that fell on the edge of the stream towards the bank. And that, being kind of a nerdy guy, that sparked an idea in his mind that that would be a way to separate the leaves based on where they fell in the river or in the creek. So he thought about how this would actually work in an analytical sense and set it up. So there's a couple of ground rules that we have to have. The particles must be much, much smaller than the thickness of the channel. So this is a picture of the Sears Tower in Chicago, which at one point was the tallest building in the world. You see people down here and you see how tall the building is. So if the building was the thickness of the channel and the people were the size of the particles, this would be something that scales about correctly to facilitate the separation. The other thing is that the flow in the channel must be Reynolds number, very low Reynolds number, essentially Reynolds 0, which causes it to be a purely laminar flow. And this is one of my favorite examples of a laminar flow system that exists on a very large scale. This is in Brazil, in the rainforest of Brazil, Amazonia. This is the Rio Negro that's coming down and it's joining with the Amazon River. The Rio Negro exists in a very densely forested area where there's a lot of biological runoff into the river, a lot of tannins and organic matter like that. So it's actually very dark in color. Whereas the Amazon is coming in out of a planar region. And so it's relatively, it's more water, less organic matter. And you can see that these two phases don't mix. We've got persistent black and blue portions of these rivers for several kilometers. So that's an example of a low Reynolds number system existing on a very on a very large length scale. We're going to look at, in this case, we're going to be using low Reynolds number systems on a much smaller length scales of centimeters to microns to centimeters. Okay, so what can we do with FFF? So we actually separate a particle based on the ratio of two pseudo-orthogonal physical-chemical properties. In the case of asymmetric flow, we're separating on the ratio of Stokes drag to diffusion coefficient, which both scale in the appropriate direction with radius. So we're basically separating on the basis of particle radius. We can separate very, very delicate, soft things that an LC system just can't touch. The most extreme example of that is we can actually separate oil and water emulsions. So something that is not too far away from salad dressing, we can actually separate those, separate the individual oil droplets based on their size. And its biggest difference is that there's no stationary phase. So the channel is a completely open channel. There's no packing, no solid phase, no stationary phase for the particles to interact with. We're purely separating particles with hydrodynamic forces. So that allows us to look at these amphiphilic structures that are very surface active and would stick down onto the stationary phase. And just to give you an idea of scales, your typical analytical LC column has a surface area of about 900 square meters. And your typical analytical FFF channel has a surface area of 0.05 square meters. And so I've made those fonts normalized to a log 10 relative scale of the surface area to give you a feel for the difference on a log scale. And we basically eliminate the surfaces. I'm an engineer by training, so I tend to try to think about these things in scaling terms. Okay. So how does FFF work? So first of all, it's going to be a channel. This distance here across is going to be several centimeters. And this distance up and down is going to be 100 microns, order 100 to order 500 microns. And what we do initially is we flow buffer from both ends of the channel. Let me go back. We'll start that video again. And then we introduce our sample here. I've drawn it now as a mixture of two species, large blue spheres and small red spheres. And we run it in such a way that the bottom of the channel is an ultrafiltration membrane that is porous to the buffer, but impervious to the particles. So the particles get focused down and they accumulate in a nice narrow band up against this ultrafiltration membrane that's at the bottom. The top here is a piece of plexiglass, impervious. And so after we get our sample introduced and focused down into this nice narrow band down on the bottom, we switched the flow profile, and now we're going to flow buffer in through this direction and out through this. So this arrow is going to change in direction. And now we set up what's called a parabolic flow profile. And so if we label a spot of fluid right here, you start to see that the fluid in the middle moves more rapidly than the fluid at the edges. And I've drawn this here where we have an impervious membrane on the bottom just to demonstrate how we set up a parabolic flow profile. Now, if we change this bottom membrane again back to an ultrafiltration membrane, something with a molecular weight cutoff of tens of kilodaltons, now we get what I like to call a beer belly flow profile, where there's a component of the flow that's going laterally, and there's a component of the flow that's going down. And so what that serves to facilitate is the small particles will have a higher diffusion coefficient, and they'll be able to diffuse up into the faster parts of the flow stream and move more rapidly through the channel. Whereas the big particles will have a lower diffusion coefficient, so they'll migrate less far into the more rapidly moving component of the flow channel. They'll move through the channel more slowly. And this is further enhanced by the fact that we have a certain component of downward force. So since these particles have a smaller diameter, they'll experience a lower Stokes drag, which will serve to push them down against the membrane with less force. Whereas the big particles have a larger diameter, they'll experience more Stokes drag. So these two things are working together synergistically to segregate the particles into different portions of the flow field and facilitate their separation. Okay, so now don't get too scared. This is a little bit of a scary slide, but don't get too scared. Once we separate the particles, now we'd like to measure how big they are. And so we do that with a technique called light scattering, in this case, multi-angle light scattering, where we have our sample in a flow cell. We shine a laser light through that flow cell, and then we measure the intensity of the scatter at several different angles around the detector. And we plug it into this equation. This comes from me scattering theory. It's an approximation called the Rayleigh-Gaines-Debye approximation, which simplifies the math a lot. And so we measure this with our light scattering instrument. This is the scatter intensity as a function of angle. This K star is just a nasty instrument constant. You don't have to worry about it. Most cases, this P theta goes to 1, so we can just ignore that. And now we measure the concentration with some kind of concentration detector, usually a UV vis, but we can use refractometry as well. You could use fluorescence, any kind of concentration technique would work. And so now we know everything we need to calculate the molar mass of this. This is now a 5th grade algebra problem. Y equals XC. And so we know this, we measure this, and then we calculate the molecular weight. When things start to get a little bit bigger and the radius of gyration becomes significant, then we actually plug in the form factor, and then we can back out a radius of gyration and actually get a physical size. The other one we do, so we have another detector that measures directly the translational diffusion coefficient. This math is just here for the edification of any mathematically inclined people there. What we do is we measure the time dependent fluctuation of the scattered light. That gives us a translational diffusion coefficient. And then through Stokes-Einstein, we can calculate hydrodynamic radius. So this is just like if any of you guys have a Malvern Zeta View, a Malvern Zeta Sizer, or any of those DLS instruments. Anton Parr makes one, Wyatt Technology makes one. It's a very old technique. It's a very common technique. It's very easy to do. You just drop your cuvette in, hit go on the instrument, and you'll get a radius out right away. Okay, so now go back to the liposomes. We started saying, okay, let's start playing with the operational space and see what happens with the liposomes that come out. And so first thing we thought is, so these things are going to be controlled by the amount of shear that they experience while they're in the fluidic channel, in the microfluidic assembly channel. And so we started out with a flow rate up here around 200 microliters per minute. And we get these liposome population dispersion here centered around 28 or so, with a full width half max at about 10 nanometers. And we decreased the flow ratio so that the shear stress is decreased by almost an order of magnitude. And there's no real detectable change in the mean particle size. There's maybe a little bit of a change in the distribution or the width of the distribution of particle sizes, but it's not really appreciable. And these data are all generated with the FFF moles detector. So that's the FFF, the asymmetric flow field flow fractionation, in conjunction with the multi-angle light scattering. With some more tricky mathematics, we can actually get particle counts. So we're looking at the number of particles per mil at each radius that were in those original samples. So then the next thing we did was, instead of changing the total flow rate, we changed the ratio of the flow rate. So the ratio of the alcohol lipid stream to the ratio of the aqueous stream. And wow, now we were really excited when we got this data, because now we have a handle where we can, at very low flow ratios, create large liposomes with a wide dispersion. And by increasing the flow rate ratio, so decreasing the alcohol flow rate and increasing the aqueous flow rate, we can create continuously smaller and smaller liposomes with a more narrower and narrower polydispersity, until we get down to what's called a size limit. These are at radius 25. That's actually about as small as these lipid formations can be. At that point, the radius of curvature gets so tight that the lipids can't pack anymore. So we were super excited. This got submitted, and we actually got a JACS article out of it. And that, so that, yeah, one of the best results we had out of my postdoc. So then we played years and years with this, optimizing it. We finally found out that if we did a sheath flow system, where now instead of having this planar microfluidic system that I described earlier, we have a sheath flow where we introduce the alcohol stream in the middle here, and we sheath the entire diameter or circumference of that with aqueous phase. Then we have a much more uniform mixing profile across the diameter or the height of the microfluidic channel. And now that allows us to create the most monodispersed liposomes reported to date. If we look at the size of liposomes that you get with the old traditional just hydrodynamic film hydration, this is, film hydration membrane extrusion. So this is the most crude technique where you just swell the lipid on a surface and then squish it through a membrane to homogenize it. You get this not bad polydispersity index, not great. If you use our first generation planar microfluidic device, you see you get a slightly better polydispersity index. But now if you go to our annular system, you see, wow, we've got a polydispersity index of almost nothing. So we've got a radius here of about 57 and a full width half max of just a few nanometers. So virtually all the particles in this preparation are the same diameter. And we can, by playing with different parameters as far as the diameter of the inner tubing and the flow rate ratios, again, we can recapitulate some of this size control with this new next generation device that actually is simpler to operate and actually allows us to operate with much higher throughputs. The planar device, we're operating with hundreds of microliters per minute. With this annular device, we're operating at milliliters per minute. So it's actually a much more scalable platform to operate with. Oh yeah, and that got us a cover article in a journal called Lab on a Chip. And one of my colleagues and myself learned how to use a graphical rendering program called Blender. And we made this kind of cool looking graphic. Because when the journal came back to us, it's like, we'd like to put you on the cover. And we thought that was really, really great. And we said, we'll need some cover art from you. And I was like, okay, who's your staff artist? And they're like, you. So with a couple of weeks of hard effort, you can learn one of these 3D rendering programs and make some really cool graphics. So basically we're showing here the alcohol focusing stream here, and then this kind of backlit cutaway of a liposome that is glowing in the dark. Most tenuously related to physical reality. Okay, so now we're going to talk about, now we've got a tool to make liposomes of controlled size. So let's see what happens when we start giving those liposomes to cells. And if there's, do cells like big liposomes, little liposomes, middle-sized liposomes, something like that. So with enough practice and time and blood, sweat, and tears, you can actually make what we call a liposome ladder. So this is a set of 6 different liposome preparations that have very, very little size overlap. So now we can start to really, really tease out what the size effects is. Before we had this tool to create monodispersed liposomes, you'd have a plurality of sizes in this preparation, and you wouldn't be able to tease out which sizes were going into which cells, because they'd all be the same. Here we have controlled different batches, so we can put this batch into a cell and measure the uptake, and we can put this batch into a cell and measure the uptake and see what the effects of size are. And so what we first did was we just looked at the liposome uptake as a function of time. and particle size. These were actually CACO2 cells, so it's a colorectal carcinoma human cell line. And as you can see, not surprisingly, the longer that you incubate the liposomes, the more that they get uptaken into the cells. And there seems to be a preference for smaller liposomes. So the smaller the liposome, the more rapidly it gets taken into the cell through whatever mechanism the cell is using. It can be some kind of passive uptake. It can be some kind of active uptake. We don't know anything about it. We're just measuring how much fluorescence is increasing in the cell as a function of time. So then we started to get, oh, okay, sorry, ahead of myself. So there's a variety of different active endocytotic pathways. This audience knows way more about this process than I do. This is a screenshot I stole off of a Nature Review article. And so we wanted to see if certain sizes of liposomes were being trafficked into the cell by these different endocytotic pathways as a function of size. So what we did was we treated them with different chemicals or drugs that are known to downregulate certain endocytotic pathways. So this first one here is monodiazyl cadaverine. And so it downregulates clathrin or receptor-mediated endocytosis because it's a transglutaminase inhibitor, which screws up the endocytotic pathway here. This one is philippin. This was extracted from a fungus that existed in the Philippines. It's a mixture of isomers of this polyalcohol, and it disrupts the disrupts the sterol binding, which disrupts the caveoli formation. This one here, this is another fungal extract that inhibits macropinocytosis because it's a phosphoinositide 3 kinase inhibitor, which blocks these, the scission of the macropinosomes. So when they're butting in there, they can't pop off and come down into the cell. And then finally, we use this other one called Dinosaur, which is a GTPase inhibitor and blocks the dynanim activity, which again prevents the vesicle scission for that endocytotic pathway. So we've got 4 different drugs that suppress different endocytotic pathways. And now we're going to treat those cells with different sizes under each of these drugs and measure how much the intake is suppressed as a function of particle size. And so you can see here that with our biggest liposomes, actually we're not suppressing their uptake significantly when we're comparing them to smaller liposomes, where the treatment with these drugs causes massive suppression in the uptake of the liposomes. So this points heavily towards these middle-sized liposomes and smaller-sized liposomes being more transported into the cells with more of these active mechanisms and not just passive cellular fusion. And how am I doing on time? Good, we're in good shape. We also wanted to look at once these liposomes got into the cell, where did they go? Did they get trafficked to the lysosome or to the endosome? So if we look here at the how many of them actually made it all the way into the lysosome, you can see the yellow is where we've got a lysosome and a liposome co-located. So you can see again with our 72 nanometer particles, we're getting a lot more of the particles going into the lysosome. Again, consistent with, but not conclusive of this being part of the active endocytotic pathways. And now if we look at the endosome location, so this is one step forward. I should have flipped these 2 slides in order. You can see that our larger liposomes now, these basically 100 nanometer particles, are now winding up mainly in the endosomes and not making it as much into the lysosomes. So I realize these are kind of crude experiments, but they're at least our first attempt at trying to tease out some of these size-dependent mechanisms. And now if we actually look at the difference in the actually quantitate the difference in the amount of material that went to the endosome versus the lysosome. So we've actually stained it with the endosome-associated protein and the lysosome-associated protein. Only actually one of them had statistical difference in where the two particle, which compartment the particles wound up in, and that's our 72 nanometer liposomes. The other ones, there wasn't enough statistical significance to establish if there really was a difference between the two. And that being said, I didn't do this work by myself, of course. So there was a postdoc working with me, Donna Amayatek. She now works for a pharmaceutical company that specializes in making liposomes as a drug delivery vehicle for antibiotics to treat advanced tuberculosis cases. Don DeVoe is a professor of mechanical engineering at the University of Maryland. He and I co-mentored a PhD student who was very talented, actually made the liposomes that we were, that I showed in those graphs. And then the people that did the cell culture and the uptake experiments themselves and knew about the different drugs to influence the endocytotic pathways is Peter Swan at the University of Maryland, Baltimore School of Pharmacy. He's the editor of Journal of Pharmaceutical Research, and one of his PhD students, Abhay Andar, who actually did the cell culture experiments. That being said, we're right at 45 minutes into the talk, which would give us a good amount of time to talk about any questions you guys might have, and anything that we can, any questions I can answer about AF4. Again, I'm a chemical engineer. I'm a separation scientist. I'm not a biologist, although Ken is teaching me. Ken and Dominic are slowly teaching me the world of EVs. And we're getting our feet into that actively now.
Great. Well, thank you so much, Wyatt, for this talk. And you didn't mention, but your name is Wyatt, and you use instruments from a company called Wyatt, and that's just such a coincidence, or is it?
Yeah, it actually. So the company is owned by Dr. Phil Wyatt, and his two sons run it now. Phil is approaching 90 years old. Brilliant man, still goes to work every day. Wyatt Technology is a company of about 150 people now. I started working with them in 1997 when they were a company of about 30 people. And no joke, when I give lab tours often, and when the NIST lawyers come through and they see Wyatt Technology written on all the instruments, and they know my name, and then they immediately think that I'm have a side company and that I'm using government resources to buy products from my company. And I have to explain to them that no, my first name and the surname of the company owners are coincidentally the same.
Coincidence. All right. Well, we actually have some questions about coincidence, if you define it in a certain way. So I think that the questions that have come up in the chat box and that have been sent to me by email are kind of grouped into a couple of categories. So the one I think is the capabilities of AF4 and what you can possibly do with it, what you could possibly use to improve it. So let me see here who we have unmuted already. I think we have Lilia. So you had a really nice question about how you might be able to change some of the parameters of AF4. So go ahead and let Wyatt know what you'd like to know about.
Okay. Yeah, thank you. That was a really great talk. And actually, it made so many dreams in my mind how this technique could be possibly used when we're talking about the vesicles from the blood, for instance, the extracellular vesicles in LDL, but so they have the different size, but they have the different region and the different the surface and so on. And I'm just wondering, when you show this microfluidic chip, if there is a way to have more than one channel and to have more than one buffer, and also to play somehow with some ultrafiltration membrane, for instance, you know, just like to kind of separate in the same time the particles by the size, but also based on their region. How would you think
By their
possible?
which?
By their region. For instance, the LDL, the lipoproteins, the light low density lipoproteins, they are monolayered and they basically differ with the extracellular vesicles that the extracellular vesicles, they're bilayered and they're phospholipid.
Oh, okay.
The same size as
Yeah,
LDL.
yeah. So AF4 doesn't care about the density of the particles. So an EV and an LDL or a polystyrene particle of the same size would move through this particular kind of AF4 at the same rate. So we wouldn't be able to separate them. Now, there are techniques that we can implement where we apply an electric field here.
Mm-hmm.
And so if there was a change in the electrical charge of the particle as a function of its composition, then we would be separating based on that. So that's called electrofaradic FFF. There's many different flavors. I just talked about asymmetric flow, but like an electrofaradic flow or a combination asymmetric plus electrofaradic would allow you to get a different selectivity where you could start to separate out the LDLs from the exosomes. Perhaps we haven't really looked at that. There was a paper by Cal Giddings, the inventor of FFF, where he separated VLDLs, LDLs, and HDLs out of either serum or plasma, I don't remember which, with this technique, and he was able to completely resolve those three lipoprotein species. But we're actually looking at doing exactly that with some of the work that we're doing with the Witwer Lab, because the LDLs can be a contaminant within your EV species, your EV preps.
Yeah. All right. Okay, thank you.
All right, thanks so much. So we have Sarah E. had a question about sizing and aggregation.
Great talk. So I was wondering, if you were to be able to use it with EVs, how would they be affected with like interaction and aggregation of EVs? Would it be possible? And a second question, if I remember my physics good, a laminar flow means the flow rate isn't really that fast, so it wouldn't cause like breakup of exosomes either?
So great question. So there's very low shear in the channel. There's a relatively sophisticated box that I'm not showing here that actually controls all of these different flow rates so that they actually happen in the way that we want them to. And those flow measurement and control technologies are only a few years old. So we originally thought we could use this to separate eukaryotic cells, and it turns out that there's some pretty high shear in the flow controller box. The flow controllers have some high shear regions, and so we were putting in something like 1 million cells and getting out like 3 that were viable. So it basically sheared the heck out of the cells. But that saying, with exosomes, we don't see that. They're small enough that they don't get enough mechanical shear to get damaged as far as we can tell. Now, the one thing that we are a little bit worried about is during this focusing step, the local concentration of those EVs goes up orders of magnitude. So even if you got a particle concentration of 10 to the 8 per mil or something like that in your sample that you're injecting, it's going to be concentrated up into like 10 to the 14 or 10 to the 15 particles per mil in its local concentration as it gets slammed up against this membrane. So that's something we do have to worry about if we're going to artificially aggregate these EVs because they're getting so highly concentrated. But I mean, because you guys use spin columns and things like that to purify these things, maybe it won't be as much of a problem. Jury's still out on that.
Great, thanks for the questions. I also had a few others that that came to me, and I think somebody didn't have a microphone, so I'm going to just ask them myself. So, are there any ways, Wyatt, that you could actually load or associate some kind of a cargo with a particle using AF4?
Could we actually put a cargo into an EV with AF4?
Yes, or associate it somehow.
I mean, we could use it as this focusing technique as long as what you're trying to load into the EV or associate with the EV is larger than the molecular weight cutoff of this ultrafiltration membrane on the bottom, then you could you'd have a local concentration enhancement that might facilitate any kind of passive loading mechanism that's accessible to put stuff either on or in the EV. But if it was a small molecule, that probably wouldn't work very well because it's just going to go through this ultrafiltration membrane and out of the channel.
Okay.
If I'm understanding the question.
Yeah, I think so. So, so the other question that came to me was, how is this? How scalable is this? Can you ever have some kind of a preparative capacity with AF4? You mentioned the different flow rates that you can do.
So there's several different channel geometries that are commercially available. Anything from something that's operating at a flow rate of a few hundred microliters per minute, all the way to operating at tens of microliters per minute. So there are preparative channels out there where you can load milligram quantities of material. The channels that I showed in this work here are medium-sized channels, and we tend to load something about 100 micrograms of material on that, and then that 100 micrograms of material gets diluted into 5 to 10 mils. We have successfully ran ribosomal particles through this and got sufficient sample out to do a multiplicity of Western blots. So you could use it for a preparative method for some sensitive analytical technique downstream. Be fun to put some EVs in here, separate them based on size, and then look to see what their marker profile is with either something like the nanosite or sorry, ExoView, or one of our Western blots or ELISAs or something like that.
Okay. Yeah, and I want to, we just had a couple more questions that come in about capabilities and outcomes. So I want to go to Kent next. Kent, I know that you say you don't have video. That's fine. You can just ask, just go ahead and ask your question.
Yeah, hi. Just curious about the practical size range distribution that you get with AF4. So I know it kind of falls between size exclusion chromatography and flow cytometry, but what would be a practical size range of particles that you could separate?
Okay, yeah, excellent question. So on the low side, what we can separate is determined by the ultrafiltration membrane. So as long as the particle won't go through the ultrafiltration membrane, that's our lower size limit. So if you're looking at something like a 1 kilodalton cutoff, we can look at particles that are diameter 1 to 2 nanometers on the low end. On the upper end, we can look at particles in the neighborhood of a micron with one operational mode. There's a second operational mode where we can actually look at particles from 1 micron all the way out to about 10 microns. So now we're getting into the flow cytometry size range. But those two, we can't operate those two modes simultaneously. We have to either be in the 1 nanometer to 1 micron size range or the 1 micron to 10 micron size range.
And then your distribution of flow rates would then regulate how well you could separate out the particles in whatever range you're looking at.
Right. So we regulate this amount of what we call cross flow. We actually ramp that from a high level to the low level. You can think of it similar to like in a reverse phase HPLC, how fast you ramp up the organic component of your mobile phase. It's very analogous to that. Or you could also think about it in terms of size exclusion chromatography. The force that we're pushing down here with the cross flow is analogous to the pore size of the SEC column. So it's kind of like we can dynamically adjust the pore size of an SEC column in real time.
Okay, thanks.
Thanks, Ken, for the question. We'll next move to Maya K. And you had a sticky kind of question.
Hello, Wyatt. Great talk. Thank you. I wanted to ask about recovery of vesicles because I experience in different concentration devices that the vesicles get sticky to the membrane. So in your cross flow and later in the rolling through the on the surface of the membrane, do you experience any stickiness of the vesicles to the membrane? Do you lose some vesicles?
The answer is yes. We do our best to mitigate that by picking a membrane that will not be sticky to the particles of interest. We have noticed that as we change the cross flow, for some particles, we actually lose more. We can actually push all of the particles through the membrane, or they get absorbed onto the membrane. We don't know which. We just know that they don't make it out to the detector for some of the more, I call them squishy, soft. And we think they're actually squeezing and pushing through the membrane. That being said, with the EVs, they tend to be a little bit more structurally sound. We also do a lot of pre-treatment of this membrane. We try to saturate it with some kind of an albumin protein or something like that. So similar to how you block on a Western blot. We do something like that here to mitigate as much of the sticking. We don't have quantitative numbers for what our recoveries are for EVs because we're just now getting into that. But for liposomes and for proteins, recoveries are in the neighborhood of 90%.
Okay, do you get any material out that is lower than your starting vesicles? Do they explode or something like that? Do you have some soluble proteins that you didn't have before?
We don't have any data for that. We've just looked at a few, they're plasma derived samples.
So you might look at some protein that is originally inside the vesicles on the outside.
No, we don't know because the preps that we've had so far have a significant amount of albumin and lipoproteins in them that elute earlier. So we wouldn't be able to distinguish that necessarily unless we collected those fractions and did some kind of an offline characterization technique like a Western or something like that to see in fact albumin or an EV associated protein.
Okay, thank you.
Great, thanks for the questions, Maya. And then we also have a question about some of the capabilities from Delva. Delva, would you please go ahead with your question?
Thanks, and thanks for your presentation. Connecting also to Maya's question, I know that the A4F, when the output of the A4F has very huge volumes, and you speaks about Western blot and other analysis performed on the output of the A4F, but eventually you have the need to concentrate those volumes.
Yes, yes.
want to work on other analysis, what kind of techniques do you use to concentrate? Because in our case, every time we try to concentrate vesicles or whatever else, they start to stick on membranes between each other. So you start to have very huge aggregates, and eventually all the works is gone.
Okay, so there's a couple of answers to that. One technique is that you could take that, that eluent stream that has your EVs in it that's coming out of the AF4 and use your favorite offline concentration technique like the synthrocon or centrifugation or something like that. There's some new technology coming out that they're developing. What I skipped over and didn't talk about, this is a higher level thing. All of the action is happening here down next to the membrane. This top part of the channel is just kind of wasted space that's used to set up the hydrodynamic flow profile to facilitate the separation. So if we could, out here at the outlet, separate and just suck off the juicy stuff down here that's got a lot of particles in it and throw away this stuff up here that's just wasted buffer, then we can get the concentration up, we're guessing 5-fold or so. That technology is just now coming out. I'm probably going to be beta testing it for the companies when it comes out. And we're very excited about that because that'll allow us to get into a concentration range that straight out of the AF4 that we haven't been able to access yet.
Okay, thank you.
Thanks, Delva. I want to conclude the session pretty soon, but Wyatt, there were actually some questions, some technical questions about the uptake experiments that you did, and I just want to summarize some of those. And you know, some people were asking about some of the statistical techniques and so on, but I think that there were a few things that would be great to clarify. The one question was, what was, again, the composition of these liposomes that you used for the uptake, and was the composition the same for each size, or was it a little bit different?
Yeah, they were the same. So these were predominantly DPPC was the component, the major lipid component. I believe they were 50% DPPC, 40% cholesterol, and then no, they were, yeah, 40-50, and then 45. They were cholesterol, DPPC, and a little bit of pegylated lipid, and a little bit of a cyanine dye. The di-IC18 was what we put in there. The composition was the same amongst all the lipids. There was no compositional difference.
Okay, so that was not contributing to the differences in uptake or distribution, presumably. So what do you think? What do you speculate might be the reason for why the different sizes are taken up differently?
Good question. We think that that just the uptake of these particular sizes are more actively utilized by these particular endocytotic pathways. Again, not being a biologist, I'm a little bit hand wavy in talking about that. But I mean, if you look at these particles that are diameter 70, they seem to be completely suppressed, whereas the larger particles still seem to be able to get in relative to what they would be in the absence of the inhibitors. So maybe there's a more of a passive component to the uptake of those.
And yet, sorry to interrupt, but I think with those 70 nanometer liposomes, you're also seeing a lot of variability there. Are you not?
Yeah. The error bars are huge. To me, they're huge.
And in fact, a lot more than for the other sizes. So that's another interesting observation here. That's quite neat. So, yeah. So in any case, it'll be interesting to see. I think there's some some biology here that still needs to be worked out.
Yeah, this has all been published. I should have the citation in front of me, but I don't. But the authors, this was the only paper that was written by this set of people.
Yeah, so if we get the permission to put this up on YouTube, then we will. We can also associate a link to the paper. So, all right. Well, at that, I think we'll conclude. Thank you all for attending our EV Club today, and we look forward to seeing you again in the near future. So thank you to Wyatt for your very clear presentation. I think we've all learned a lot today, and I think that some of us will be using this technique more in the future. So thanks, everybody.
Thanks, guys.
Hope to see you soon.
Taking the time to listen.